Hey everybody, we are going to continue into circuits by talking about resistance. Now, when we have current flowing, the electrons are bumping and vibrating and running into atoms and other electrons. And how much of this bouncing and vibrating and, running into atoms depends on the structure of the material that these electrons are moving through. And so again, if you remember from current, the motion of electrons is kind of sporadic. They're bouncing all over the place, going kind of crazy. And how much of this bouncing and jostling around depends on the material that they are flowing through. So when we're talking about this bumping and running into things, we're talking about resistance. And so resistance is a measure of how difficult it is for current to flow through a material. It also kind of tells us how much energy is transformed and transferred from electrons bumping into things. We know that the purpose of electricity is to transfer energy. And so as the electrons are moving, they're running into things, and we know that collisions transfer energy, and that's what's happening when electrons run into things. All materials resist the flow of electrons. Conductors resist a lot less. Insulators resist a lot more. Superconductors resist not at all. You get them cool enough, you cool their temperature down enough, and there is no resistance. Semiconductors can actually change their resistance. Now, when we measure resistance, we measure this in a unit called ohms. That is abbreviated with the uppercase Greek letter omega. We use the variable letter R when we're representing resistance in math problems. So if I wanted to write 5 ohms of resistance, I would write R equals 5 omega. That's the abbreviated symbol for ohms. Now, what affects resistance? Materials have specific resistivity due to their atomic structure. So different things like copper or silver or rubber, they all have different levels of resistivity. Something that is more resistive is going to be a good insulator but a poor conductor. It's not going to allow charge to flow very well. And these are things like rubber, glass, dry wood. Those are good insulators, not very good conductors. They are highly resistive. Things that have low resistivity, they're less resistive, those are going to be great conductors, poor insulators. Those are things like copper, silver, gold. Those are things you'd want to use for wires to transport electricity. Besides its resistivity, what could you do to a material like, say, copper? What could you change about it to get it to change how much resistance it applies to current, to moving charge? And there are a few factors. Length is one of those factors. So if you have a longer wire, there's naturally more stuff to bump into. It's going to be more resistive. So shorter wires are less resistive. Longer wires are more resistive. So if you've ever used extension cords, the longer the extension cord, the heavier duty or the thicker the gauge or thickness of the wire is because of that added resistance due to its length. So, again, longer means more stuff to bump into. If you thought about it in terms of moving through crowds, would you want to move through a crowd of people in one room or a crowd of people in 10 rooms? You add more rooms, more people to bump into, right? Now, I mentioned the gauge of wire, the thickness of wire, and that's another factor that goes into resistance, the width of something, or the width of a conductor. If the wire is wider or thicker, there's less resistance. You're giving more pathways for the electrons to flow. It's like widening the freeway or making the water pipe bigger. There's more options, more pathways. It's easier to flow through when you have a thicker material. Temperature also plays a role in resistance as well. Higher temperature means more resistance. You may remember that when something's a higher temperature, it has more internal kinetic energy, which means there's a lot more vibrating and jostling. Translational kinetic energy, meaning the kinetic energy of molecules running into each other, is basically what temperature is. And so when you have a higher temperature, you have more of these collisions. That's going to increase resistance of a material as well. So higher temperature, more resistance, cooler temperature, less resistance. And that's why when you cool down a superconducting material, its resistance basically goes to 0. So why resist? What is is there anything that comes out of resistance that is useful? Absolutely. When the electrons are bouncing and bumping and vibrating, this uses up their energy. If you remember the demo that we did in class where we took two metal spheres, collided them together, and we burned a hole in the paper, by those collisions, we were transferring energy. We were actually transforming the kinetic energy into thermal energy and transferring it to the paper. Some things are designed for this. So light bulbs, for example, or heaters, computers, televisions, anything that has the need for electricity is actually counting on this to happen, because as those electrons move through these devices, they are transferring some of their energy, and these devices are actually resistors in themselves. So an example is an old school incandescent light bulb. Pretty much everything's LED these days, but an older LED or an older incandescent bulb works off this process where electrons will flow through the filament, and the filament is a very thin wire. So remember, the thinner the wire, the more resistive, and when you have enough current going through this wire, it starts to get very hot. And not only does it give off heat, so we have a transformation of the electron's kinetic energy into thermal energy, but we also have a transformation into light energy as well. And that's the whole point, right? We want a light bulb to light up, and that's exactly what's happening due to the resistance of the bulb. There are other devices called resistors, and these things are designed to specifically reduce the amount of current in devices. Electrical components make use of these to protect the components from too much current. Could you imagine running the amount of current that it takes to start your car through your cell phone? That would be bad. So resistors are components that can actually reduce the flow of electrons to help protect electrical components, and that energy from the electrons is simply transformed into thermal and released into the environment. So a quick summary of resistance. What is it? It's basically telling us how difficult it is for current to flow through a material. We measure it in units of ohms, represented by an uppercase Greek omega. The math letter that we use, or the variable letter that we use in formulas, is the uppercase R. And the factors that affect resistance are the length of the object, the width of the object, and the temperature of the object. If you have any further questions on resistance, please don't hesitate to ask. Thank you for watching, and have a good one.